In this video, we'll talk about solving systems of linear equations, specifically 2x2 systems. Start with a definition. A system of equations is a set of two or more equations that must be solved simultaneously or at the same time. Given two linear equations in two variables, we are looking for the ordered pairs that satisfy both equations. Remember that an ordered pair is a solution for one equation. It's a point on the line. So if we're looking for solutions that work for two lines, we're looking for the set of ordered pairs that live on both lines. If we were to graph two lines on the same set of axes, the points of intersection would represent these solutions. We have three methods of solving systems that we'll cover in this video. The first one will be graphing, the second will be substitution, and the third one, elimination by addition. So giving you a graphical overview of what possibly can happen when you're graphing two lines on the same set of axes. The first case is what we're kind of hoping, not necessarily hoping would happen, but this is probably the most common case, where we have two lines that have different slopes and live in two different locations, and then at some point those two lines will meet at some place. If you have two lines that do not have the same slope, eventually they will intersect. So that point of intersection represents one solution. In this case, we would call the system consistent. If it's consistent, that means that it has at least one solution. And we would call this case independent system because the two lines each have different solution sets. The solution set for this line is different than the solution set for the other line. So consistent means at least one solution, independent means different solution sets. The second case is if we have two lines that are parallel to each other. So if you recall, parallel lines have the same slope, and because they have the same slope, they will go on infinitely and never intersect each other. If they don't intersect, there's not one point that works for both lines. This would be a case of no solutions. Because there are no solutions to the system, we call the system inconsistent. Inconsistent meaning there are no solutions. The third case is if two lines actually end up getting graphed in the exact same location. So it looks like we have one line here, but this is actually two lines that are graphed, but they have the same equation. So maybe at first the equations don't look like each other, but after manipulation or after graphing them, you might recognize that the two lines actually coincide. Coincide means that they're exactly the same. In this case, we would have infinitely many solutions. Every single point on the line represents a point on the other line as well. Because there is at least one solution, there are infinitely many, but because there's at least one, we would say that this is a consistent system. And because the two lines have the same solution sets, they are in fact the same line, the system is dependent. So when we're graphing, we're looking for these three cases. All right, so let's take a look at the first one. We have x plus y equals 1 and x plus 2y equals 0. So for my first system, I see that I have my two equations. Neither of them are in y equals mx plus b form, and I like to have that form. I think it's easy for me to graph. You might also decide to use x and y intercepts to graph as well. So I'm going to write this system out on my paper. And you know, maybe I will, that first equation, maybe I will use x and y intercepts. Why not? So one quick and easy way you can find x and y intercepts is by covering up one of the variables. Because the x-intercept occurs when the y is 0, I can make the y 0 by just putting my finger over it. So for this line, and you know what, I like to sometimes label my equations as well. It just helps me to keep track of my work. So I'm going to call the first one 1 and the second one 2 using Roman numerals. So for my first equation, the the x-intercept, which occurs when y is 0, so I'm covering up the y because it's 0. I have an x-intercept at 1, or I could think about that as an ordered pair, 1, 0. And a y-intercept occurs when x is 0, so I can cover up the x. So it has a y-intercept also at 1, but on the y-axis. So that would be the point 0, 1. So I could go ahead and plot those 2 points to find that line. So let me go ahead and do that here. So on my graph, I'll just use a scale of 1 in each direction. So let's say here I have 3. This would be -3, +3, -3. All right, so my first equation has a y-intercept at 1 and an x-intercept at 1. So my line would be the line that connects those 2 points. When you're graphing systems, it's really important to have an accurate graphing system. So you want to use graph paper and a straight edge if you're doing it by hand. This is my first line. All right, for my second equation, I could maybe use intercepts again, but maybe I'll put that one in y equals mx plus b form just so you can see something different there. Let me get my graph out of the way. So for my second equation, I'm just going to solve that for y, subtracting x from both sides. Then I have 2y equals -x plus 0. I don't need that plus 0, it'll leave it there for now. Dividing everything by 2. And I have y equals, I'm going to write this in fraction form, -1/2x, and then 0 divided by 2 is still 0. So in this case, I would have a y-intercept at 0, and my slope would be -1/2, so that's down 1, 2 to the right. So let me go ahead and draw that line. So I'm beginning at 0, my y-intercept is 0, and from there I'm going down 1 and 2 to the right. Down 1, 2 to the right. Down 1, 2 to the right. Okay, so once again, using my straight edge, connect those points. Having more points is helpful when you're connecting. And this is my second line. All right, now, this is a nice graph. It's nice and neat. I have nice straight lines, but the graph alone isn't what I need. I really want the point of intersection. And even though I've drawn a nice graph, my point of intersection is a little off there. So it looks like it's about here. I might want, it could occur at a fractional point, but the examples that we usually see are usually integer or maybe sometimes fractional values when you're graphing it. So most likely I was a little off graphing that blue line, and it's probably this point here. Probably. Now how can I be sure? Well, I can just check it to make sure that works. So that point of intersection is the point 2, -1. Now, if that is a solution to the system, then it works for both equations. So I'm going to check it in both equations and see if it works. So let's go ahead and check here. So I am checking 2, -1. If you're not going to check both equations, don't even bother checking, because checking one equation is not going to help you. So I'll check the first one. Replacing x and y with 2 and -1. So 2 plus -1, is that equal to 1? Well, 2 plus -1 is the same as 2 minus 1, which is 1. So 1 equals 1. So that works. So it works for the first equation, but it's only a solution if it works for the second one as well. My second equation, x plus 2y equals 0. So the x is 2. X plus 2y, my 2 is, my y is -1. Is that equal to 0? 2 times -1 is -2. So this is 2 plus -2, or 2 minus 2, which is 0. So it does work for both equations, which means the solution to this system is the point 2, -1. I'll practice writing this solution in set builder notation just so you have an idea of how that looks. So here we're looking at the set of ordered pairs, the set of all x, y, such that x is equal to 2, comma, y is equal to -1. And that's how you could write your solution set in set builder notation. All right, let's take a look at the second system, which I have here. Separate that a little bit. So for this, I'm going to go ahead and write both equations in y equals mx plus b form. So I'll call that 1 and I'll call that 2. Let me go ahead and pause and do that for a moment, save some time. All right, so I went ahead and rewrote both of those equations in y equals mx plus b form, and you have that here. So you can pause and take a look at the work on the screen if you need help getting those equations in that form. So now I'm going to go ahead and graph each of them. The first one has a y-intercept at 1 and slope of 1/2, positive 1/2. Let me get my graph over here. So I have a y-intercept at 1, slope of 1/2, so up 1, 2 to the right. I'll do that a couple of times. I can even go down 1 and 2 to the left. Now you might have noticed, either looking at my work or doing it yourself, that these two equations have the same slope. So if you notice that, you might recognize that these two equations are parallel because they have the same slope, but the y-intercepts are different. So for the second equation, I have a y-intercept of -1, but also a slope of 1/2, so up 1, 2 to the right. So once you recognize that your two lines are parallel to each other, there really isn't a need to go ahead and graph. I'm just going to continue to graph just to convince you that they are parallel to one another. The graph is just a way to get your solution set. So if along the way you recognize that your solution set is empty, you can go ahead and state that. And again, that's because our two lines are parallel, their slopes are the same. So in this case, I would have no solutions. So we could just say empty set. And I could write the symbol for empty set. Why not? We're using our set builder notation there. All right, our third example here. Again, neither of these equations are written in y equals mx plus b, so I'll pause again, go ahead and put them in y equals mx plus b form, and then meet you back here. Okay, so just like magic, I took both of my equations and I solved them for y. And again, you can pause this and take a look at the work just to make sure and verify that you're comfortable with solving for y. So what I noticed is when I've solved each of these for y, I have y equals -3x plus 1, and then again, y equals -3x plus 1. I went ahead and identified the y-intercept and the slope as 1, and then the slope is -3 over 1, so it's down 3, 1 to the right. But both of these equations map the same line. So I went ahead and I graphed that line as well. So here we have a line, has a y-intercept at -1. You can fit that on the screen here. So began at 1, and then down 3, 1 to the right, down 3, 1 to the right. And doing that for the second equation as well, we get two lines that live in the same place. So this means we actually have infinite solutions. These two lines are dependent. They have the same solution set. So we have a special way to write that in set builder notation. We have the set of all x, y, set of all ordered pairs, such that, so now we need to write my description. So x can be any real number. X can be anything, right? We could pick any x value and we could get the y value. How do we get the y value? Well, the y value is determined by x. So we just take one of our equations written in y equals mx plus b, and we just rewrite it. Y equals -3x plus 1. So this tells me that no matter what x is, the y can be found by going through those steps. And that's how you would write your solution set in set builder notation. But again, that means infinite solutions.